Hello, welcome to today's seminar for the second time. Our speaker today is Ping Hu. He got his PhD at University of Illinois, Urbana-Champaign. His advisor Yoshi Balog, and then he was a postdoc at University of Warwick. And now he's transitioning to
associate professor in China.
Okay.
But it's not
China, someplace in China.
Yeah.
Okay, and he will be speaking about tiling graphons, to joint work with Jan Hladký and Diana Gue.
So thank you for the introduction. So I want to talk about tilings in graphons, and if you're not familiar, I will define graphons in the first few slides. And for tilings, it's just you want to find vertex disjoint copy of a fixed small graph. Like if you want to find vertex disjoint copy of edge, then it's matching, right? And you can find all others. But during this talk, I will mainly focus on matching for simplicity. Okay, so let's first look at the graphons, what it is. So you study graphs, and for a lot of problems, you are not studying some, say, exact properties of a graph. You are studying large graphs, and you are studying approximate, or say asymptotic properties of large graphs. So in this way, it makes sense to somehow, in some way, study the limit of large graphs. And and related objects are something like a flag-order method, property testing, but I won't talk about that in this talk. But all of those things are just, for example, study the asymptotic property of large graphs. For example, property testing says like if your graph, say, is very large and you want to check just small pieces, and say, for example, you want to test if the graph is triangle free, and you want to test only small pieces of a large graph, to say if you test enough, and you can claim the graph is with high probability triangle free, something like that, and or you can say it is far from triangle free. And so basically we say, okay, so you have a large graph and you want to study asymptotic property, so maybe you can define some limit object of this large graphs, or say a sequence of large graphs whose size go to infinity, and the limit object, which we'll define later, is called a graphon. And why we want to study that? Because it will be analytic. So graph is a combinatorial object, right? So it is discrete. But if you study the limit things, it will be an analytic object, and you can use tools from, say, analysis to study it, and which in turn will give you asymptotic property of the graphs. So you have more tools to play with. That's why we want to study that. So, and we say the limit of large graphs, right? So we want to first define what is the limit means, the convergence. We say a sequence of graph is convergent if you look at the induced density, which is DHG. Basically, you say, okay, you randomly pick some vertices, and you look at this vertex, give you the induced graph you want. For example, if, say, here DHG, H is an edge, then it's just the edge density. Or H is a triangle, then it is, say, you randomly pick three vertices, then this vertex give you a triangle. But here, it is induced subgraph, it's not just subgraph. Okay. So like if you look at cherry, then it has to be three vertices, give you exactly two edges. And we say a sequence is convergent if this induced density sequence, which is a sequence of numbers, so you have a well-defined convergence for that sequence, is convergence for every edge, every graph edge. Because the graph Gn, well, n be the number of vertices go to infinity, so this is well-defined. If the size of H is, say, larger than G of n for some small n, then the density is, you can just define it to be 0. But it doesn't matter because n will be eventually large enough, so you'll have a well-defined sequence. Okay? So it's a convergent definition thing. Okay. So now we have a sequence of convergence sequence, and we may look for some examples. For example, and here we first see some. So from the definition you can see this sequence must have some common properties, right? And usually you can define it in some way that there is a formula or something you define it. For example, here you look at a sequence which is just a complete graphs. and it converges because, say, you look at, I mean, you can check it yourself. Like if you look at anything, right? You look at the graph H. If H is not a complete graph, then it's always 0 induced density. And if H is a complete graph, then it's always 1. I mean, if your graph is, if the complete graph is larger than H, right? So it's converged. And it's also true for random graph GMP, because for example, if your H has say I don't, like say your H is say cherry, then the density will always be just p squared times 1 minus p, right? So you look at 3 vertices, and you look at the property that it gives you 2 edges, 1 and 1 non-edge. And 2 edges is p squared, and 1 non-edge is 4 minus p. So you can see, so it's, well, so for those good things, it is not actually convergent, it's always the same. I mean, except for the little of one thing. So it's, but this definition is true, is actually defined for dense graphs. But you can also embed this definition to, say, sparse graphs. By sparse graph, I mean it has only little o of n square edges. But the problem with sparse graph is any sequence of sparse graphs converge with this definition. And why? Because because if you look at any small graph and you look at the density in a sparse graph, then it is always little o of 1, which means it always converges to 0. So the sequence always converge. So in this way, you are not able to see, say, any structure of the graphs, right? That's why this definition only makes sense for dense graph. Because for dense graph, you have a limit object, which we'll define later. From the limit object, you can actually see what is some properties of the graph which convert to the limit object. But for, say, sparse graph, although you can see those sparse graph looks something common, and you can look at some others, and you can even mix them, but whatever sparse graph, a sequence of sparse graph is always converged. So you cannot see anything about the limit about the sequence of graphs. You can only say it is sparse graph. So it doesn't make sense for sparse graph. That's why we say it is dense graph converged. Okay. So, okay, and now let's define the limit object. So a graphon. A graphon is a measurable function from 0, 1 square to 0, 1. And it has to be symmetric. And actually it is, you will see later, it is just, you can in some way, you can think about it as a limit object of the adjacency matrix. Okay? So for example, like say here, if you have a bipartite graph, it will be, okay, so I should say, so 0, 1 square, right? So you think about 0, 1 like here and here. So this is the origin 0, 0, and 0, 1, and 0, 1, okay, instead of the usual axis. So you can see here, so bipartite graph means you have vertices here and vertices here, for example, you can think about that, and then you have edges here and here. And W random graph means from such function, you random pick n vertices along the line, 0 to 1, and 0 to 1 here, the same vertices, say xi, and you look at and xi, xj is an edge with probability the value of your function, w of xi, xj. Okay, and so in this way you got the random graph. Okay. Any questions? No. And you can see here, and actually, so here, this, well, you can see it. You can see, like, say here, you break the, so for example, this one, you break the vertices into 2 parts, right? And say this is A and B, and you can see here, you have edge between A and B, right? So that's why you have A here and B here and all edges between them. So that's why it is bipartite. And here you can think of this is A and this is B, and you can see you have edges inside A and inside B, which means it is 2 clear. Okay. So 1 means you have an edge, and 0 means none. You do not have edge. If you follow from the W random graph definition. But now, let's see. So we have the induced density of a graph from in a graph, right? And here you can define the induced entity of a graph H inside from a graphon, which is just a probability that the both W random graph of is just H. Okay. And we say W is and then we say it converge if the sequence, this sequence H, the induced entity of H in Gn converge for every H, and it converges to the limit object W such that the induced entity of H in W is actually the limit of this. Yes.
So in order to understand your third bullet point there, are the vertices ordered and then H has to occur so that x1 and x2 line up in the same
Right,
order?
so if your H is ordered, you can order H in whatever way, then
Sure.
it is ordered. Yeah.
But then it's fixed, and you're asking the question is, if the graph occurs in the order, so you're choosing random, yeah, so it occurs in the order in which you chose the xi's, or doesn't it matter at all?
Let's see.
I think this
I
is
think
the
it's
unlabeled
just
federation.
it's just a labeled or unlabeled version. So if in the unlabeled version, then it doesn't matter.
Okay.
Yeah, so,
Otherwise, it's off by a factor, like
yeah.
blah, the automorphism group over n.
Right. So we say, okay, so a sequence is converged, say Gn converge to W in the limit, then you know that actually the limit of the densities for any H induced density also converge to the density in XW. And we have some good properties. So you may look, okay, you can already read, but you may wondering like what sequence of graphs converge, right? And so in the real study, right, in the research, you got a sequence of graphs. How do you say it's converge or not? But sometimes for example, you got a sequence of graphs with good property. You don't want to check if it's converge or not, but you can say it's always, as long as the size go to infinity, which is a term increasing means, it always have a convergent subsequence. So for example, in your research, you build a sequence of graphs that have some good property you want, and then you just say, okay, it has a convergent subsequence. And then this convergent subsequence also have the good property you want to study, and it has a limit object, which you can study the limit object to know the graph you want to study, for example. And every convergent sequence of graph has a limit. And also, from a graphon, you can see the graphon itself, the definition has nothing related to the limit itself, right? It's just a measurable function, symmetric. But if you take a sequence which is a W random graphs, then it converges to W, which means every graphon comes from some limit. It's a limit of some sequence of graphs. Okay. So just summarize. So you got any increasing sequence of graphs, the size go to infinity, it has a convergent subsequence, and which converts to a graphon. And you give me any graphon, it comes from a sequence. It will be a limit of some sequence of graphs. Okay. So that's some basic things. And let's look at some examples. And as I said before, you can think about graphon as a limit of your adjacency matrix. For example, like say here you have seen before, you have a bipartite graph, and the adjacency matrix will look at like this, right? So 1 denotes an edge, 0 denotes an edge, and then 1, 1, 1 become black, and 0 become white. And the same for this. But you may wondering, right? So this is not the only way to write the adjacency matrix of a bipartite graph. You can permute the vertices, right? And which will not give you exactly the same as this. So yeah, so I cheat a little bit the definition. So we say two graphs are isomorphic if you just permute their vertices and they give you the same graph, right? So we say two graphons are isomorphic and vertices the same if you have a micro-preserving map on the 0 and 1, which is basically the vertex set. Okay, and you give it the same graph. And also another example is this. So a sequence of random graphs, say Gn 1/2, it is random, and then this time your graphon is not have value just 0 and 1. This time it is a constant graphon 1/2. Okay. And maybe a quick quiz. What is a graphon which is the limit of sparse graphs? Will be what?
It's an all white.
Yeah, just of 0. Yeah. So map 0, 1 square to 0. Okay. And you can see because it's a 0 function, you have no information from the sequence. Okay, so let's look at the problem I want to study. Actually, it's not this one, but the next one. So let's see. So you have know the density of graphs, right? So you may think about that. So in extreme, like say combinatorics or graph theory, you study something like this. So you have some condition, say G has a certain number of edges, okay, and G is large. Then you want to say, okay, how many clicks it has? Say, for example, one question is, if a graph has, say, a certain, like say E or alpha n half number of edges, so alpha here is the edge density, then what can you guarantee me how many triangles it has? Right? So turn out this problem is quite hard. Okay, so if alpha is 2, then it is trivial, because it's an identity function. But if alpha is 3, then it is proved by Rutherford 2008 using flag algebras, and which also have some ideas from dense graph limits. Because you can see this problem, right? So you look at G, which is a large graph, and you want to study the density of KR in it. So if you look at the limit object, it's exactly the same problem, right? You look at a graphon which has alpha edges. The edge density is alpha. Remember, we have defined the density of any graph inside the graphon. You can have a graphon of edge density at least alpha, and you look at the KR density inside the graphon, which will be the function GR. And for alpha equal to 4 means you want to study the K4 density. It is proved by Nikiforov using weighted graphs and some analytic methods. And for general all clicks, it is proved by Retter 2016. And it is inspired by graph limit using also weighted graph method.
What do the curves look like?
So it is like this. So it is just so the graph itself is just multipartite. So it looks like Turan graph, but it's not balanced. So if the edge density is Turan density, then it is Turan graph. Between two Turan density, it is multipartite. It is multipartite, but with not balanced part. You want to have the right part sizes corresponding to the edge density you have.
Okay, so all of the constructions along the
The same.
optimal curve are imbalanced multipartite graphs?
Yes. So that's one example.
Okay,
So
but it's
so
not the-
basically, so you have a multipartite graph. Okay, so that's one extreme example, and you can change so it is multipartite, right? So you can change two of them, which is a bipartite graph, right? So you can change that bipartite graph to any triangle-free graph with the same edge density. Okay. So you can see this problem, you can use, say, graph limit method to study. And, but what about another kind of similar question? Again, you're giving the condition is the edge density. But this time, instead of looking at the density of a click, I'm looking at how many vertex disjoint click I can have, which is a tiling problem. Okay. And turn out this problem is quite hard. Okay, so for alpha equal to 2, what it means? It means I give you edge density, and I'll ask you, what is the maximum matching size you can guarantee? Okay. And for alpha equal to 3, so this one is proved by Aldrich and Galai, and for alpha equal to 3, it's proved by Allen, Bocher, Halasky, and Pigot, which means you give me edge density alpha, at least alpha, and I want to ask you how many vertex disjoint triangles you can guarantee. Okay. And of course, it is a density, so you don't need to care about the little of 1. Okay. So again, this is large graphs. So we somehow want to use some ideas from graph limit to study such problems. Okay. So that's the main inspiration of this research. So we have seen here, so the density problem is easy to transfer to graph limit language. You have a sequence graph, which the limit is a graphon W, and the KR density is GR alpha, the limit is just GR alpha. So you just study this graphon W, and if you get this GR alpha function, you know it is the same function. So, and you have well-defined density here. But what about tilings or the vertex disjoint or something? Let's see here, right? You have a graph which is n copies of K2, which itself is a perfect match. Unfortunately, it is sparse graph, right? So the limit is, as you said, 0, which means whatever way you define the tiling number or the matching number of a graphon, this should always give you 0. And this is a perfect matching. So you do not have this limit. So you need to do something more. Okay. So let's look at the definition of graphs. And just to, I believe most of you or all of you know, but let's just quickly go over that. So a matching is a set of vertex joint edges, and the size is just the number of edges in the matching. And we say the matching number is a maximum over all matchings of G. Okay. And you can also define fractional matching. This time you are not looking at a set of disjoint edges, but you have a function from the edge set to 0 to 1, and you give a weight for every edge, such that for any vertex, the sum of the weight of edges incident to that vertex is less than or equal to 1. And the set of a fractional matching is just a summation of all the weights. And again, the fractional matching number of G is a soup of all possible fractional matching. And the fractional matching is a general version of matching, because for matching you can think about this function is from E to only 0 and 1, instead of all possible numbers between 0. Okay. And so you can see here, because you have only finitely number of choice for matching, so this is max. But for function, you have infinite many, so this is 2. Okay, you will see this later. So let's look at example. So triangle, and it's a very easy example. So the matching set is 1, and right, and fractional matching is 3/2, because you can assign 1/2 for each edge. And its graphon is like this. Okay. You just think 3 verses, like say 3 verses, and you have like edges like this. Okay. What about I blow it up? I blow every vertex into say n verses, and then what's the matching number? This time it is 3n over 2, because you can have n-half edges here, n-half edges here, n-half edges here, and they won't touch each other. Okay. And the fractional matching is again 3n over 2. And because it's a blow up, so it gives you the same graph. You can see here, so let's say here A, B, C, D. Okay. So what does this? What does this give you as some inspiration? The inspiration is for graphon, there is maybe no difference between a matching and a fractional matching, because somehow graphon itself denotes large graphs, and for large graphs, there's where you think about it like denote a blow up of some graphs. And for blow up, if your blow up is large enough, then there's no difference between the matching and fractional matching. Okay. So we define the matching like this. So first, it has to be a function which is greater than or equal to 0, and for each x, which means which corresponds to the vertex, and this time you do an integral instead of summation. So basically this definition is come from the fractional matching, and instead of the matching, because I said for graphon there should be no difference between the matching and fractional matching, and we just follow the idea of fractional matching from graphs to graphon. Okay. So this time, instead of you have so for fractional matching you have a function on the edges, And here you have a function on omega square, or you can just think about it as 0, 1 square. And it is a non-negative function, and for each x, you do the integral along the vertical line or the horizontal line. It should always less than equal to 1. Okay. And it should only, so before we say f is on the x side, right? So this time we say the sup of f is in the sup of w, which means basically says, so it should not define on the where it's no h or say w is 0, because it makes no sense. Okay. So basically it's completely, you borrow the idea from fractional matching proof.
Okay, so why is that not, why don't you also impose the condition that f is less than or equal to w?
Because
if something's like a half edge.
it makes no sense to say less than equal to w, right? So basically, so actually here, we don't care about, so think about it, we don't care about the value of w, right? So like here, I have a complete multipartite graph here, right? I said the matching number is 3n over 2. But if I have a random graph here between these two, I like between those places,
Okay,
right?
then that's still the right number.
Yeah, it
of
should
edges.
it
That's the
always
number
give
of-
you
okay.
3n over 2. So it actually doesn't matter the value of your w here, right? That's why you don't, so as long as you have some non-negative value, then yeah. So that's, yeah, so you can see, so actually, so here we don't actually, so the definition itself does not depending on the value of w. It only, you only care about where w is not 0. Okay, so let's look at the example. So this time I'm not looking at a optimal matching, fractional matching, but let's see what is will be. So this time I have 0.6 here, 0.3 here, 0.4 here. You can see it is a valid fractional matching because the summation is always less than to 1. And I want to transfer it to a matching in the graphon here. And how I do it? You maybe first write it down. But see here, the idea is, say 0.6, say this 0.6 here, right? So it is a weight on this edge. But here, instead of the function, it should be the integral. The integral of this function here will be 0.6. And the integral of this function here will be 0.4. Which means, and what is, so, okay, so if the integral is 0.6, then what is the value here? Should be. This is 1/3, right? So just 1.8. So you just multiply by 3, right? So if you multiply by 3, it is 1.8. Then you do the integral here. Means you can do the integral either this way or this way. It doesn't matter. You have integral on an interval of length 1/3, so it will give you 0.6. Okay, and the same for all others. So if after you do the integral, it gives you the original number. But this is just a case where your graphon comes from a simple graph, right? So it may not look like exactly like this, but so this is just a showcase that the definition makes sense. Questions? Okay. And again, we have the side, which is the integral of the function, and here divided by 2 just to normalize, doesn't matter. And the matching number is, again, because we are looking at functions, there's infinite many of them, so it is the sup of f, the size of f, over all possible fractional matching. Okay. And I use sup. So for example, you have your f along here, right? And if you do the integral here, this will give you 1. But if you do integral, for example, here, it will only give you something like alpha, right? So along this line, most of the time you got integral 1, but around the corner you got some small numbers. So it is actually, so after you do the integral, it will be a number very close to 1, but less than 1. And and because of this, if you look at the soup, it is 1. So it means you have a perfect matching, and actually, so this graph, so if you look at the graph coming from this graphon, it is basically you look at verses, say 1 to n, and and the I and j have a number if the sum is less than equal to n plus 1. Okay. So you have a graph, say n verses, 1 to n, and two verses have an energy if it is less than equal to n plus 1, and then you have a perfect matching if n is even. So basically 1n, 2 and n minus 1, and so on. Right? But this is the only perfect matching, which corresponding to this diagonal. But
square root of 2.
Sorry?
I mean, then you just need to integrate the area of that strip. So do you get square root of 2?
No, you got 1, I believe. Because you see here, most of the time you got 1, right?
Oh, okay, right.
So the problem is around the corner you won't get 1, so it is slightly less than 1. But if you take the soup, but you can be close to 1, yeah, arbitrarily. So the soup is 1, but you cannot attain the 1. Okay? And you can prove you cannot attain. So the soup is not necessarily attained by some fractional matching. Okay? So convergence. So this bad example says you do not have the same convergence as the density of graphs, right? So you have a perfect matching converge to 0. But we do have convergences, it is greater than equal to. So you look at the matching number of the graphs, and if it converges to a graph in W, then the matching number, the limit of your matching number is greater than equal to the matching number of W. And it is actually good because most of the time you want to guarantee a lower bound on the matching, right? You want to say, okay, I have a graph. I want to say what is the size of matching you can guarantee, right? So it is actually good. You look at the limit object of your graphs, and you get the matching number, and it provides you a lower bound.
Because you have an example that provides the upper bound.
Yeah. And also, like, if you have a graphon, a sequence of graphon converges to W, I haven't defined it yet, but you can think about from, but it is just a function graph, converge to a function. So, and again, you have the greater than equal to. The lim in is greater than equal to the matching number of W. And we want to study more. We want to say, okay, so this is a bad example, but is it in some sense the only bad example? So in some sense means, so why this is bad? Because this is a perfect matching, but if you just change a little bit of the graph, it becomes 0, right? You just change a little of n square edges, remove all edges basically, then it is an empty graph. So we want to say, okay, is this the only trouble we have, the only reason we do not have equality? So we define a robust matching number, means instead of just looking at the matching number of the graph itself, you are allowed to remove a tiny bit. Okay, so from G, you remove a tiny bit, which is, say, less than equal to epsilon n square edges, and then you look at, if I remove a little bit, what's the matching number I can guarantee? For example, in this, it is just 0, although it is because remove epsilon n square edges, it is empty. And the same for graph on W. You remove something which is tiny, means the value is less than equal to epsilon. And then you look at the matching number. And in this way, we have equality. Means in some sense, this is the only bad thing we have. So if you have somehow a graph which is robust, means you remove just a tiny bit of it, you still have the relative, it has the same matching number or like really close to your original graph, then you have equality here. Okay.
And
question?
in the first definition of robust matching, you're deleting edges.
Yes.
Yeah, but the vertex set is the same.
Yes. So you delete the subgraph, which has just little edge.
Because that's consistent.
Yeah. And in this way, you have you minus a function u, which is less than equal to w. Okay.
The theorem, is that for every epsilon, fixed epsilon greater than 0, then those two statements hold?
Yeah. Epsilon should be small. Yeah. Okay. And so for matching, we have LP-duality, right, between the matching and the vertex cover, which you can see easily from LP-duality versus the LP linear programming, because you look at the fractional matching problem. It is the maximum of, you have a function f, you want to maximize the sum such that for any vertex, the summation is less than equal to 1, and also the value of f is greater than equal to 0. If you think about this is a primal problem, and you look at the dual, it is exactly the fractional vertex cover problem. You are, so instead of, so you look at the dual means for each condition here, you have a function g on this vertex v, and you minimize vertex v, and for any edge, u plus gv is greater than equal to 1, which is the coefficient of f here. And for any vertex v, gv is greater than 0, which is exact the definition of fractional vertex cover. And LP-duality says this is the same. Okay, so I believe you all know the definition of fractional vertex cover, which is exactly this. And LP-duality says they are the same. Fractional matching number of a graph G is the same as the fractional covering number, a vertex covered number of G. And we want to have something similar for our definition of matching of graph. Means we want to have also vertex covered of graph. And we see here, we say, again, it is a function on the vertex side, which means here you are looking at omega, which is a base set of the graphon, or say the 0, 1. You can just think about it, C as 0, 1 to 0, 1 is a fractional vertex cover, if, which you borrow the idea from the fractional vertex cover of a graph, says for almost all xy, if wxy is 0, then cx plus cy is less than 1. So wx means if it is not covered. So what is covered? Okay, so what is cover means? Cover means the sum is greater than equal to 1, right? So means it is covered. So if it is less than 1, means it is not covered. Then almost always w is 0, means it is not an edge. Okay. Means, or you can think about it the other way. If w is greater than 0, then cx plus cy should be greater than equal to 1 for almost all xy. And the set of C is just the integral. And the fractional cover number of f is the inf over all fractional cover. And this time, we can actually show some properties somehow nicer than the matching, but we start from this here. We say, if you have a convergence sequence of graphon Wn converge to W, and the Cn is a fractional vertex cover of Wn, then any limit of Cn is a fractional vertex cover of W. Means you have a convergence sequence of graphon to a W, and then from the sequence you have a, for each graphon Wn you have a fractional vertex cover. Then you can take a limit, and it will be the fractional vertex cover of W. And why this theorem is good to give us some nice results? Because First, it says the lim in is greater than or equal to the fractional cover number of Wn is more than fractional cover number of W. But more importantly, it tells us that the fractional vertex cover number is attained by some cover. Well, for the matching, we say we have example say it is not attained. Why we have fractional number is attained by a cover number? Sorry, because you can just say W, take Wn. Okay, so here we have a sequence of Wn approach, the limit is W, right? And to prove this corollary, you just take all Wn to be W itself. And then, see here, we say it is inf, right? Which means you have a sequence of fractional vertex cover whose limit is a number of your fractional vertex cover number of W. And then you just take a limit of this sequence, and it will give you the desired one with that number. Okay? Any question? So you just take Wn to be your W. Every Wn be your W. So of course it converts to W. And then you take the sequence which give you from the inf definition, the limit should give you the right number, and then this theorem tells you that the limit of that sequence is a fractional vertex cover giving you this number. Okay? And we also have the theorem says, like the duality says, the fractional vertex cover number of a graphon W is the same as the matching number. So why this one is good? Because we say the matching number may not attain by some matching, right? But then we can say, okay, it is the same as the fractional cover number, and it is attained by some cover number. So then you have an example, you have a concrete object which can give you that number, and you can study that concrete object, which is easier than studying the matching number, because there may be no matching attain that number. You can only study a sequence. Okay. Let's see how much time.
5 minutes.
Okay, I'm too slow. Okay, so let's look at one quick application. So remember we say, give me a graph on W, I can sample verses to give me a sequence of random graphs, right? Okay, this is just, and we have the theorem says, if for that sequence, it actually, so remember we say, okay, if a sequence of a graph G converts to W, then you can only have you do not have equality. You only have, say, the lim inf is greater than or equal to the matching number of W. But this time, I'm not looking at any sequence, I'm looking at exactly this sequence, the random graph coming from the W. And then we can prove that the limit is actually, the equality holds for the limit. If you look at this sequence of graphs coming just from the graphon, it converts to W, and also the matching number, fractional matching number, also converts to the matching number of W. And the proof is actually quite, okay, I should have enough time to cover the proof. So by the theorem, we have one side, right? We are already on one side, so you only need to prove the other side. And we will use the cover number to prove the other side. We say, okay, we fix a fractional vertex cover C of W, which gives you the extreme number. We already showed it such C exists. And then we can also have a fractional cover C prime of each G and W, such that it is not far away from C. Okay, and then you got the other way. So here, so the fractional matching number of G and W will be bounded by C prime, which is bounded by the set of C plus epsilon, where C is, well, this achieves the number, so it is bounded by the matching number of W plus epsilon for any epsilon. And then, because it is true for any epsilon, you prove the other inequality. Okay? Questions? I hope this time is not too fast. And I have another application. I will just quickly go over it. So, Komlos theorem says you want to find, again, the condition this time is not giving me the edge density condition. This time is give you the mean degree condition. and you want to study how many vertex disjoint property of F, okay? Which is a tiling. And the general example is this. You have a almost multipartite one, and and you have a complete graph here, and you have, say, not complete graph, some random graph, not random, some arbitrary graph here. Some arbitrary graph here, and this size may be smaller than the other one. So what Komlos proved is he proved this function, and using our method, we can prove that actually this is a general example. Or say we prove that like a stability version. We say if your graph has roughly this number of vertex disjoint F, then your graph should be not far away from this extreme. Okay, so that's all. Thank you.
Questions? So you are showing it for matching, but the same can be done for like 2 regular or 3 regular graphs as well?
For let's see.
Yeah, that's harder.
Yeah.
I don't know, I'm asking.
So
You can say it's harder than...
So it's, we actually can, I believe we have a generalization which can be done for any basic, because because it's a vertex disjoint, right?
Mhm.
So it really, so as long as you have it is a small graph, it's fine.
Okay.
So you don't have to be, there's no condition on the graph itself. Just the generalization is more technical, so I don't want to show it. So for example, let's see, is it here? Yeah, for example here, right? So let's say, for example, if your graph is on surfaces, then your function is not on omega squared, so it will be on omega cubed.
Okay, so you say you can tile with graphs that have bounded size.
Yeah. So you fix your graph. So you want to study, say, for example, tiling of graphon with some. You want to fix your small graph, say a cherry or K4 or cycle, something of some fixed size, and then you can have a certain definition for the tiling of that thing in a graph. But it's more technical definition.
Other questions? Okay, not let's think again.